So for the first problem, we'll be determining the effective nuclear charge for different electrons in the palladium element, as well as the electron in cadmium, and then from there, figuring out why cadmium has a larger ionization energy than palladium. And so to begin, we first need to write the electron configuration for palladium to help us determine which electrons will be relevant in determining the shielding constant, and then from there we can determine the effective nuclear charge. And so to remind ourselves, the effective nuclear charge is Z subscript F is equal to the nuclear charge of the element minus S, which is the shielding effect caused by the electrons in lower energy levels, as well as those in the same atomic orbital. So for the first part, we'll be determining first the electron configuration for palladium. So if we pull up a periodic table, we see that palladium is here. And so we can use the periodic table to determine the electron configuration for palladium. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, and 4d8, because we have 8 valence electrons in the d orbital. And so now that we've written the electron configuration for palladium, we can then rearrange this so we know which electrons we need to use to determine the shielding constant. And so we need to rewrite this so that all of the atomic orbitals of the same energy are grouped together. And so we have 1s2, 2s2, 2p6, this is one group, and we have 3s2, 3p6, and 3d10 grouped together, as well as 4s2, 4p6, 4d8, and finally 5s2. And so for this problem, or specifically for part A, we need to figure out the effective nuclear charge for an electron in the 4p orbital, and so that means that everything that is to the right of the 4p orbital can be disregarded, and so we don't need to worry about the 4d as well as the 5s. And so now we can use Slater's rule to determine the effective nuclear charge for an electron in the p orbital. And so to do this, we know that if we have electrons in the same energy level, in this case the energy level 4, each electron will contribute a shielding constant of 0.35. And so since we're working with a specific electron in 4p, that means the 5 other electrons will contribute to the shielding constant. And so we have 2 from the s orbital and 5 from the p orbital. And so we can multiply this by 0.35. And if we plug this into our calculator, we end up with a value of 2.45. And now for the next energy level, each electron will contribute a shielding constant of 0.85. So that means we have 2 from 3s, 6 from 3p, and 10 from 3d. And so we can multiply this by 0.85. And so if we plug this into our calculator, we get a value of 15.3. And lastly, if our energy level is equal to or less than 2, that means all of the electrons contribute a shielding constant of 1. So we have 2 from 1s, as well as 2 from 2s, and 6 from 2p. And so we simply need to multiply this by 1. And so this will give us 10. And to determine the shielding constant, we need to add all of these numbers together. And so we have 2.45 plus 15.3 plus 10. And so we get a final shielding constant of 27.75. And now we just need to plug it in to our equation up here. And so the effective nuclear charge is equal to 46, which is the atomic number of palladium, minus 27.75. And so if we plug this into our calculator, we end up with a value of 18.25, which is your final answer. And now for part B, we need to do something very similar, except we'll be calculating this for 4D8. And so we can simply rewrite the electron configuration that we figured out from before. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d8, and 5s2. So again, for the electrons that are in higher energy levels than the atomic orbital that we're interested in, we can simply ignore this. So 5s2 will not contribute to the shielding constant. And so we'll need to figure out the shielding constant for the electron in 4D. And so because the electron is in 4D, Slater's rules are a little different. So those in the same atomic group will have a shielding contribution of 0.35, and everything else, in other words, the lower energy atomic orbitals and electrons in lower energies will have a contribution of 1. And so if we have the same group, this means that we have 7 electrons contributing to the shielding of the last electron. So we have 7 times 0.35. And so if we plug this in, this is 2.45. And so for everything else, we have 2 from 1s, 2 from 2s, 6 from 2p, 2 from 3s, 6 from 3p, 10 from 3d, 2 from 4s, and 6 from 4p. And so if we add these together, we end up with a value of 36. And so if we determine the shielding constant, this would be 38.45. And so if you were to determine the effective nuclear charge, this would be 46 minus 38.45. And so you end up with 7.55, which is your final answer for part B. And now for part C, we will determine the effective nuclear charge for an electron in the 4D orbital for cadmium. So if we look at cadmium really quickly, it is actually in the same D block or in the same period as the palladium, except it has 10 electrons in 3D. And so we know that it has basically the same electron configuration, except we have 4d10. And so we can simply just figure out the shielding constant for the same group and then use the numbers previously to figure this out. And so you know that for the same group, we have 9 times 0.35. And so this ends up being 3.15. And I'll just write this in a different color so it doesn't get lost. And so we have S is equal to 36, which is all of the other electrons in the lower atomic orbitals as well as the lower energy orbitals, plus 3.15. And so that equals to 39.15. And so the Z effective is the nuclear charge, which is 48 minus 39.15. And so we get a final answer of 8.85. And so to explain why cadmium has a larger ionization energy than palladium, we can simply look at the shielding constants. So we actually see that the Z effective for cadmium is greater than the Z effective for palladium, which means that the cadmium has a stronger pull on the valence electrons than the palladium, and so that means that more energy is required to remove an electron from cadmium versus palladium, which explains why it has a greater ionization energy.